This lesson is going to be looking at what happens when your exponents are 0 and negative. So let's take a look at this. So if we have 7 to the first power divided by 7 to the first power, 7 to the first power just is 1 7. So that's really 7 over 7, or 7 divided by 7, which equals 1, right? But if we use the division property of exponents, remember, if we're still doing the same problem, 7 to the first power divided by 7 to the first power, our base stays the same, but our exponents, we take them and we subtract them, right? So that would give me 7 to the 0 power. Now, these two things are exactly the same problem. So if this one up top equals 1, this one down here should also equal 1. So this one is easy rule to remember, because anything that's not 0 raised to the 0 power is always equal to 1, because your numerator and your denominator will always be the same, and you can cancel them out to make the pairs of 1. So anything to the 0 power is always 1. Now let's take a look at something else. So if I have 7 to the 4th power, that's 7 times 7 times 7 times 7. And it's being divided, or it's over 7 to the 7th power. So 7 times 7 times 7 times 7 times 7 times 7 times 7. Okay, so just like when we did before, we made the pairs of 1s. So that became a 1, that became a 1, that became a 1, that became a 1. So when we found out what it equals, our base stayed the same, and then we have our exponent. So I have how many that are left? 3, right? But the 3 is on the bottom of the fraction, or the bottom of the division problem. And remember, all of these up top here all canceled out to be 1. So our answer would be 1 over 7 to the 3rd power. But if we look at that same problem using the division property of exponents, we could keep our base the same, so it would stay 7, but we would subtract our exponents. So 4 minus 7 gives me negative 3. So what happens when we use a negative exponent? What happens is that we keep the base and the exponent, except the negative means that it sends it to its opposite location. So right now, if I were to make 7 in the negative 3rd power a fraction, it would technically be over 1. So I just have to send the exponent down to the bottom, because when we simplify exponential expressions, we do not use the negative. So the negative just tells us that, like up top up here, that the 3 7s that are left are in the denominator of the fraction. So let's look at this one. We have 5 squared, which means 5 times 5, over 5 to the 9th power, which is 9 5s. Okay, so then I make my pairs of 1s, and then I have how many 5s left over? 7s. So I would have my 5 to the 7th on the bottom, and then I would have this left over on the top, which those canceled out to be 1, so I would have 1 over 5 to the 7th power. And if I did it using the division property again, I would subtract my exponents, 2 minus 9, which equals negative 7, and because it's a negative 7, it tells me the 5 to the 7th power is going to be located on the bottom of the fraction. So let's take a look at these couple of examples. If I had 2 to the 4th power, that's 2 times 2, which is 4. 3 to the 3rd power means 3 times 3 times 3. 3 times 3 is 9, times 3 is 27. 5 to the 2nd power is 5 times 5, or 25. Now, these problems on the right-hand side of the screen are exactly the same as the problem on the left-hand side of the screen, except that they're negative. So if I go 2 to the negative 2nd power, remember that negative brings it to the bottom. So it's really 1 over 2 to the 2nd power, which is equal to 1 over 4, because 2 to the 2nd power is 4. Again, same thing here. I would take my 3 to the negative 3rd power. The negative 3rd power sends it to the bottom, and I would have my 1 up top. So I would have 1 over 27, because 3 to the 3rd power is 27. And then 5 to the negative 2nd power, again, the negative power sends it to the bottom, so I have 5 to the 2nd power on the bottom, and then I have my 1 up top. So I would really have 1/25. Let's take a look at this that pulls some of the different properties of multiplication and division together. that we've been looking at so far. This looks kind of intimidating because there are a lot of exponents and a lot of bases that are different. So my recommendation to you is to split them up. So I want to keep the like bases together and then treat them like they're their own individual problems. So if I'm looking at the 2's, I have 2 to the 5th power over 2 to the 2nd power. My base would stay the same, but because it's division, I'm going to take my exponents and subtract. So 5 minus 2 equals 2 to the 3rd power. Because 2 to the 3rd power, the exponent is positive, that stays on the top. So on my top of my answer, I would have 2 to the 3rd power. I want to do the same thing for the x's. So I would have x to the 4th power over x. And remember, when there's nothing written as my exponent here, we assume that it's a 1. So my base would stay x, but then we're subtracting again because it's a division problem, so I would have 4 minus 1, which would give me x to the 3rd power. Because again, the x is, or the 3 is positive, the x to the 3rd power would go up top. I want to do the same thing for the y's. So I have y to the 7th power divided by y to the 10th power. I keep my base as y, and then my exponents I subtract. So 7 minus 10 gives me y to the negative 3. So that negative tells me that I need to put my y on the bottom. And I don't need to write the negative because I'm putting it on the bottom. So I have y to the 3rd power on the bottom. And then lastly, I would have my z's. So I have z to the 9th power over z to the 4th power. My base stays z, and then I take my exponents and subtract them, so I have z to the 5th power. And because the 5 is positive, z to the 5th power goes on top. Now, you could technically simplify one more thing on this further. You know what 2 to the 3rd power is. 2 to the 3rd power is one of those ones that we have in our list, which is 2 times 2 times 2, which is 8. So I technically could say my answer is 8 x to the 3rd power, z to the 5th power over y to the 3rd power.